Equals 180 degrees.
Yes, pi radians equals 180 degrees. Okay. What do you say?
He was like, good, buddy, good. Yeah, Mr. Fair.
I'm like Trump, to be honest.
So, if I've got degrees up top, where do degrees need to go in the... Okay, so 0, or not 0, there's a degree symbol down here, 180 degrees, right? Okay, so what goes on top? Pi radians. Okay. Degrees cancel out. Left with radians as a unit, so I know this is the only conversion factor I need. How many times does 45 go into 180? 4 times. So leaves me a 4 on the bottom. So now I've got 1 times pi, which is pi. And on the bottom I have 1 times 4, which is 4. So pi over 4 radians. Is that okay?
Yep.
Okay, now I want to show you something that is going to be of benefit for us to understand when we're dealing with our calculators. We've done this before. You haven't dealt with radians, but you've heard me say in geometry, you heard your algebra teachers tell you when you did this in Algebra 1 or Algebra 2, when using sine, cosine, and tangent, you need to make sure that you are in the correct mode. You remember hearing that?
Yes.
Okay, so if I just want to demonstrate here what we're talking about here. If I'm in degrees, okay, and I type in sine of 45 and hit enter, I get that number right there. Okay. Now we will have it'll probably take a couple days to describe what's going on with your calculator and what it's doing to get that 0.707. But it's basically saying that no matter what right triangle you are inside of, if there's a 45-degree angle, the opposite side divided by the hypotenuse will always divide out to 0.707. No matter how big that triangle is. That triangle can be as big as a piece of paper on your desk, or it can be the size of Wyoming. It doesn't matter. If it's an angle of 45 degrees, the opposite side divided by the hypotenuse will always evaluate to be 0.707. Yes?
Yeah, what mode do you want to type in?
Okay, that's what we're talking about right now. Okay, so what did I type in? I typed in 45, right? 45 in my problem was a degree. Okay, so if I want my calculator to evaluate correctly, I need to know what unit my information is in. Okay, so sine of 45 degrees. Now here's the thing. Here's why this is different. Because we just said that we just said 45 was the same thing as pi over 4, right? So the argument then is that I should be able to type in pi. Where's my pi at? Pi over 4. Okay. Now here's the thing. Because 45 and pi over 4 are identical, I should be able to hit enter and get the same number. But what happens? I don't get the same number, right? Because right now, my calculator is thinking pi over 4. If that was a decimal, it'd be whatever that decimal is in degrees. Does that make sense? So to get that same 0.707 number, I need to go to mode, go down to the radian, hit radian, get out of there, second quit. Now if I hit sine of pi over 4, now it gives me that 0.707. Does that make sense?
So what do you want it as?
Okay. Well, you have to pay attention. This is the thing. I just want to make sure we all understand this. I'm going to say this today. I'll probably say it, I don't know, 10, 15 more times. But eventually I'm going to stop saying it. You have to pay attention when you grab your calculator and you're going to evaluate with your calculator. You have to pay attention to the unit that you're typing in. If you want your calculator to evaluate at 45 degrees, your calculator needs to be in degrees. If you want your calculator to evaluate at pi over 4 radians, your calculator needs to be in radians. Okay? I have given tests and quizzes in the past where somebody has, maybe we got 35 points worth of material and I get zeros out of 35. But I look at their work and they did every single step right, except for they used their calculator in the wrong mode. Does that make sense? So we have to be aware of that. We have to be cautious of that. Okay. Now I'm not I hope I've demonstrated this. Now, I'm not a jerk. I'm not gonna. If you do that, I'm not gonna give you GR35. I will do your work. I'll look at your information, and if you're using consistently the wrong mode, maybe you'll get like -5 for the whole page. You won't get -35. Does that make sense? Okay. But eventually, guys, that does become a very problematic thing. Okay.
Why do it get so dark?
It just turns off. And we'll talk about where these numbers come from later on, but that's what we're thinking about here. And the idea is, guys, if I were I'll save that comment for later. Never mind. All right, so if I'm starting with 3 pi over 4, 3 pi over 4 is that radians or is that degrees? That's radians, okay? What do I need to multiply by so that radians cancel out? It's got to be degrees over radians, right?
Yeah.
Okay, now, and this could happen from time to time. They might not, you see here, I didn't write RAD right here, right? For the 3 pi over 4. They don't always do that. They don't always write radians. They don't always, if they just have 3 pi over 4, a lot of times we have to make the assumption that because there is not a degree symbol, because that symbol is not showing up, it must then mean that it's got to be in the other unit, which is radians. Does that make sense? Okay. Some textbooks are cognizant of that and always write RAD. Some textbooks never write it. Some textbooks are 50-50. Okay.
What's ours?
I don't know. So, 180 degrees goes with pi radians, right? Okay, so what's going to happen with these pi's?
Cancel out.
Cancel out. What happens with 180 and 4?
5.
How many times?
No.
You already did it up here.
45.
45.
5.
So it's 3 times 45 then. 135. So it's in degrees, 135 degrees. Now think about this. Think about this. How does, there's 2 separate answers, but it's 2 different questions, but we can still make some comparisons here. How does pi over 4 and 3 pi over 4 relate? 3 pi over 4 is what compared to pi over 4?
Bigger.
3 times bigger, right? How does 135 relate to 45? 3 times bigger. Okay? So those are linkages that maybe can help you do these problems a little bit quicker. When we, if I ask you to take, and this is just all dimensional analysis stuff. If I ask you to take like 10 miles and change it to kilometers, okay, you can do that, right? And I ask you to take 20 miles and change it to kilometers, you can do that, right?
Yes.
But wouldn't your answer of that 20 kilometers, or 20 miles converted to kilometers, be twice as big as the answer that you had when you converted 10 miles to whatever kilometers? Because 10 and 20 were twice as big, right? That's the same idea going on here. Okay. 150. What do I need to multiply by?
Pi rad over 180 degrees.
Good. Okay. So the degrees cancel out. What goes into 150 and 180 evenly?
10.
Okay, what else? If 10 goes in, so that those cancel out, right? What goes into 15 and 18 evenly? 3. Okay. So it ends up being 5 pi over 6. And I know the units of degrees canceled out, so I'm gonna write radians.
Wait, so that calculator thing you showed us, that doesn't matter right now?
Not right now.
Okay, that confused me really much.
I wanted just to demonstrate how what do we mean by these things being the same. I wanted to demonstrate an application of showing that through some process, if I use 45 degrees, that's great, that works. If I use pi over 4, great, it works. Does that make sense? But I gotta be aware of how my technology uses that. Now 21 pi over 3. 21 pi over 3. Okay. These earlier ones, guys, these are ones that we're gonna see these so much that you're gonna commit those to memory. 45 degrees is pi over 4. 135 degrees is 3 pi over 4. We did yesterday pi over 3 was 60 degrees. We did pi over 6 is 30 degrees. Eventually you're going to figure out, 2 pi over 3 is 120 degrees. 4 pi over 3 is, 240 degrees and so forth. You're going to know these things like the back of your hand eventually, okay? But some of them, like 21 pi over 3, you're not going to know, okay? Some like, so the degree measurements that we are going to be very comfortable with eventually are going to be multiples of 30. So 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, and 360. You're going to be very comfortable with those. You're also going to be comfortable with 45, 90, 135, 180, 225, and 315. You're going to be very, very comfortable with those measurements, and you're going to know those by memory. Other ones, like multiples of 15, you might not know. So 15 degrees, you might not know. 30 degrees, you'll know. 45 degrees, you'll know. 60 degrees, you'll know. 75 degrees, you won't know. So if we don't have them memorized in 2 to 3 weeks from now, this process is always the route you want to go. You always have this conversion ability as kind of your safety net to go from degrees to radians or radians to degrees.
Why wouldn't we just simplify it to 7 pi?
You can. So Sabrina's asking, why don't we just simplify this to 7 pi, right? You can do that. Let's actually change. I didn't think about that when I wrote this. Let's make it so we can't simplify. Let's go 22 pi over 3. Blaze, you have a question?
Yeah. Are you gonna give us like negative ones?
Oh, absolutely. What's a positive times a negative? Let's do a negative one. It's not going to change. It just makes it negative. It makes your answer negative.
Oh,
okay. Let's keep this positive because I want to use this answer here in a moment to show you a segue into the next idea. So what do I need to multiply by?
Degrees over rad.
Okay, degrees over radians.
Sounds really good. God, fine.
All right, so pi is going to cancel. 3's in there are going to cancel, right? So it gives me 60. What's 20 times 60? 1,200. So what's 2 times 60? 120. Okay. So isn't this going to be 1320? 1,320 degrees. Now, here's the thing. Is that between 0 and 360? Is that an angle that we have become accustomed to? No. So before yesterday, when we talked about angles between 0 and 180, yesterday we made the jump. Okay, let's go from 0 to 360. I don't think that's a big jump. Something hopefully we can justify. But now 1320, we're going to make a big jump. Okay? And the idea that we can talk about angles that are as big as you want. If you've ever watched the Olympics, you watch skating, you watch the X Games, you watch anything where they are spinning, okay? They'll say that this person just did a 720, right? What does that mean?
Like 360.
How many times? 2 times, right? Okay. So when I say I did a... So here's the idea. If you are the person doing a 360, let's say that you are standing, we're at a bird's eye view right now. You're looking down on this person and that red dot is their head. Let's say that they are looking right now down the positive x-axis. If they did a 360, when they're done, they come to rest, are they still looking the same way?
Yes.
Yes, okay. When they do a 720, that would be 2 complete revolutions. Are they still looking the same way?
Yes.
Okay. So if they did a 1080, are they still looking the same way?
Yes.
Okay. So right now, let's just do this. Let's go. We did 1320. I'm going to remove 360 from it. Okay. What's 1320 minus 360?
What is it called? 880.
It's 960, isn't it?
Oh dear.
960.
Okay. Subtract 360 again from that.
600.
Subtract 360 again from that.
240.
Okay, so
Negative 120.
I'm going to stop at 240 because that's between 0 and 360. So what happens here in this, so this first subtraction is the idea that I did one complete 360. This subtraction is that I did a second complete 360, right? This subtraction is that I got to this final complete revolution. But now 240 means I go 180 degrees there and now another 60. Does that make sense? So that would be my terminal ray. Does that kind of make sense to everybody?
Yeah.
You did 3 complete 360 degree rotations, and then you did 240. Okay. So here's what we want to talk about. Even though that 1320 is the number that is being asked, and that's what we would type into WebAssign when they ask convert 22 pi over 3 into degrees. 1320 is what we want. But eventually we're going to do something else with that 1320. This kind of gets us kind of moving our way into the next idea here. I want to know something about 1320. I want to know, let's say, the sine of 1320. Now, your calculator can do this, okay? But what we're going to find out that a majority of this class is about is being a little bit more efficient than what our calculator is able to do. So we'll do a lot of this stuff kind of in our head without a calculator. And I don't want to evaluate anything less than 0. Actually, I don't want to evaluate anything for the sine function, essentially, that is bigger than 180 degrees. And ultimately, probably even bigger than 90 degrees. I don't want to do that, okay? But what we can find out, if I ask the calculator to take sine of 1320, so I'm going to go make sure I'm in the right mode. Go to degrees. Why do I have to go in degrees?
Because we're dealing with degrees.
Because that's the unit I have. So I got 1320, I type that in. Okay, so sine 1320 and hit enter. Okay, and I get that number back. And we'll talk about what that means, but all it essentially means is that the opposite side divided by the hypotenuse of a triangle that has a 1320, I don't want to say triangle, but essentially a triangle that has 240 degree angle in it. I don't even want to think about that really. I want to think more about a triangle that has a 60 degree angle in it, is going to be 0.866. And we'll get those angles that I just transferred over to, you will understand eventually. Okay? But I want to show you that, well, if I would take sine of, we first subtracted 360 from that, right? And got 980. Is it the same? Did we get 320? 960. There you go. So I'll go sine of 960. Doesn't give me the same number.
Yeah.
I want to go sine of 600. Doesn't give me the same number.
Yeah.
I want to go sine of 240. Doesn't give me the same number.
Yeah.
So here's the idea. If I had 1320 as my angle, it's going to be a little bit easier for us to work eventually with sine of 240. Okay? So we want to be able to basically take that number and transfer into that. And the way we did that is we just subtracted values of 360, right? Yep. Down until we got a number between 0 and 360. Now, eventually what this class is about is I don't even want to deal with that number. Sine of 240 is nasty. Okay? So what I want to do is I'm actually going to do this. I want to take negative sine of 60. Okay? And so eventually you're going to be able to visualize that when I have a 240 degree angle, I'm thinking of a 60 degree angle. Okay? And the idea of that is if you look at just this angle right here, isn't that 60 degrees?
Yeah.
Because we had to go back 240, right? So from here, this last one, this was 240. Well, that's 180, right, to there. And go 60 more. So if I go sine of 60, hit enter, doesn't give me that same number. Yeah, okay. So those are little kind of foundational building blocks that we're going to go throughout this course to make our arithmetic more efficient and easier. Okay? But what I want to show you guys is that no matter what, okay, let's take an angle of, give me an angle measurement, give me a number. 7. Okay, so if I have an angle of 7 degrees, or actually let's go,
77.
okay, so if I go 7, I'm going to take and add 360 times K to that, and I'm going to let K be an integer. So adjust this, so let's go 50-50 increments of 1. So that allows this K value to just slide around and be just an integer, right? No decimals or anything like that. So what's going on here when I do this, so Blaze gave me an angle of 7 degrees. When I make K go to 1, that is rotating back around 1 time back to that 7 degrees. Does that make sense, everybody? So he said, let me just kind of give you the picture here. He said he wants to talk about that angle as 7 degrees. Well, if I start with that ray right there, and I rotate it around itself 1 complete time, doesn't it get to 367 degrees? Does that make sense? So 7 degrees is the same thing as 367. Okay? Well, if I let K go to 2, that is actually moving, come on, twice around. So it gives me the 727. Does that make sense, everybody? Okay. Now, here's the thing with GeoGebra. GeoGebra right now, when it sees these numbers, when I type it into like sine or cosine, the argument right now is going to be viewed as a radian. Okay. I don't know if there's any way that I can go around that other than maybe, I'll see if I can do it here in a moment. I don't know if I put that degree symbol in there, if it will do it or not. But what I'm going to do basically is I'm going to just take B, and I'm going to, because B is an angle measurement, right?
Yeah.
Well, if it's in degrees, right? Can I multiply by pi over 180? And that number right there is the same in radians as that number is in degrees. Does that make sense?
Yes.
Okay. So if I go sine now of C, I get that number right there. I'm going to go out a couple more decimal places. Okay. But as I move K around, does this number here ever change?
No.
So what this is evaluating right now is that the sine of 1447 is the same as the sine of 7. Does that make sense? It's the same as the sine of negative 353. It's the same as the sine of negative 713. Is that okay with everybody? So the argument here is that we're trying to prove, we're trying to show, is that no matter how big your angle is, you have the ability to dwindle it down to a number between 0 and 360 and work with that number instead. Does that make sense? Okay. Now I do want to, just before I move on, just so it's, because it's fresh in my mind, sine of B, if I put that symbol in, what's that give me? Yeah, it does do it. That's easier. All right. Okay. So what does that get us to? That gets us to this idea here that we talk about standard position and coterminal angles. Okay. We kind of mentioned yesterday what standard position was. Standard position is taking the angle that you're interested in and letting your initial ray be the positive x-axis. Okay. So if we look at all these images here, each one of these, each initial ray is right there, right there, right there, and right there. Does that make sense? Okay. The terminal rays are the blue ones. Okay. Now, when we draw our terminal ray in like the first quadrant or something like that, we like to show or demonstrate with this little arc here, okay, the amount of movement that our ray, our terminal ray has made. Does that make sense? Because if I look over here and I just, let's do this. If we were over, oh, large. If I don't have these red markings in here, okay, that image in C looks just like the image in A, doesn't it?
Yeah.
Okay, so I would think that the angles are identical amounts. But when I draw in those red arcs, now it's showing me that this angle here might have been, like let's just say this angle here is 40 degrees. This one here, that's still 40 degrees. Okay, that right there is still 40 degrees. But this shows me I've moved 360 more than that, right? So this should be 400 degrees. That makes sense, everybody?
Yeah.
Okay. So we like, and when we're showing, especially rotations that are bigger than 360, we like to show those little curls or spirals here to show how many times we've actually revolved around the entire coordinate plane. Does that make sense? Okay. But that's standard position. What you find out though, okay, when I do look at that one and that one, if I overlap them, if I lay them on top of one another, are their terminal rays going to match up?
Yep.
Are their initial rays going to match up?
Yep.
Okay, so when something does something together, when things work together, we use a prefix of co. Does it make sense? Okay, and here they end at the same spot, or they end together at the same spot. So we refer to these as coterminal angles. Okay, so coterminal angles are two angles in which both the initial ray and initial ray and terminal rays coincide, or they overlap. Okay, but one is bigger than the other. So like 40 and 40, we really want to call those coterminal angles. They're the same angles. Does that make sense? Well, 40 and 400, they're coterminal. Okay, 400 and 760, they are coterminal. 40 and 760 are coterminal. Does that make sense? So what they ask us to do eventually is find angles that are coterminal with some provided angles. I'll get you a printout maybe tomorrow, or I might send you an email or whatever. You can do a quick Google search of it, of the Greek alphabet. Okay. For the mere fact that that's going to be a pretty common tool for us in labeling things. So you guys remember back into like geometry, you know, we call it, and we'll still use this to a certain degree. But remember calling that angle BAC?
Yeah.
Okay. Remember calling that angle A? Remember then having issues if I had that and now I can't call it angle A anymore, right? So I had to call that by 3 letters, because if I say angle A, there's actually 3 angles at angle A. But then we say, okay, well, let's make it a little bit easier. Let's make that angle 1 and that angle 2. Let's put that notation in there. And that worked, that's fine. But occasionally somebody might make the error and say, oh, well, that angle is 1 degree. Instead of that angle, that 1 is a name. Does that make sense? So in eliminating that, what mathematicians have done is in trigonometry, and then from here on out in pretty much every course that uses this information, instead of calling angles by 3 letters or angles by a number, we use a Greek letter instead. It's just another symbol. Does that make sense? Just like 1 is a symbol, 2 is a symbol, A, B, and C are symbols. Theta. Okay, so I don't know if you guys ever dealt with theta before?
Yeah.
Okay, that is theta. Okay, just some common ones that we use, and they just represent angles. And then basically, when you ever deal with a Greek letter right now until you get into more advanced math classes. You're going to make the assumption that it's going to probably talk about an angle. Okay, you start getting into other calc courses, you start getting into like differential geometry and that kind of stuff. Your Greek letters represent other things. But theta, does anybody know what this one is?
Let's start.
Sigma.
Tetra.
Well, let's do this one. Maybe you know this one.
Alpha.
That's alpha. Okay, so you Bible people, what would this one be then? Nobody knows?
What's it start with?
What'd I say Bible? Alpha and Omega?
Oh, I know.
Ever heard that? Okay.
Isn't that like
Some of you said beta. So beta is a B, but it's got this little thing that it like hangs down. So that's beta. Gamma.
gamma? I remember that.
Okay.
Pi.
Pi.
What's sigma?
That's rho.
What's
We've got. You guys ever see that one? We'll use this one in this class at some point.
yeah, it's like wavelength. Whatever.
Okay. Is yeah. Lambda. Just thinking some other ones we might use.
Alpha, beta, sigma. And then there's
Sigma. So lowercase sigma is that.
isn't there one that's like chi? I'm just thinking all like in the fraternity.
Yeah, chi is.
Monsters University.
So chi is like that, I believe. It's like that's a little X. So I'll print out a. So there like our alphabet. There's capital letters and lowercase letters, right? So that lambda I was showing was the lowercase. That sigma I showed you was lowercase. Uppercase sigma you guys have seen. That's uppercase sigma, right? Okay. Delta. So I will, like I said, I'll print one of those out. So those are common letters and symbols that maybe I'm not going to say memorize all of them. Okay. I don't know how many Greek letters there are. I know there's not 26. It's a smaller alphabet than ours. Huh? No. But theta, the theta is like the number one like go-to. So in algebra, what is our go-to symbol? What's the number one go-to symbol in algebra? X. So the number one go-to symbol in trig is theta. If you go look at your calculator right now, you see right here
Where?
on your key that is X.
Oh,
Do you see there's a theta on there?
I can't get to it. The circle with the line?
Yep. Okay. And that theta can be used or determined when I go to mode. And we'll use this a little bit eventually. But if I go to mode, and now you see down here where it says function, parametric, polar. And we'll do some of this stuff later, but this is just kind of open your eyes to some of the things that we might mess around with in this class. If I go to polar, I'm just going to write like 7. If I hit that key right there, you see how it puts theta in now, right? Instead of X. Okay. Let's just see what that graph looks like real quick. That's kind of boring. Let's go y equals 7
7?
sine of 2 theta. Let's do that.
Is it theta or how you say it?
Theta.
Theta?
Yeah, kind of boring still.
Oh.
But we'll mess around with that kind of stuff. Mess with my window, it'll change. But what happens is when we deal with polar coordinates, we get really neat looking graphs sometimes. Okay. But theta, that's just a symbol. Okay, so kind of a lengthy discussion about that, but they want us to find coterminal angles. Well, coterminal means that they are the same
Like
ending spot, right?
okay.
Okay, so I like to draw a picture here. Okay, if that's 30 degrees, which is my theta, right? How many degrees do I need to rotate that to get back to itself?
360.
360. So if I add 360 to the 30, I get
390.
390, okay? So my coterminal angle, I'm just going to call it alpha right now. My coterminal angle is equal to 30 plus 360, right? And that give me 390? Let's call that alpha 1. What's another one? Alpha 2 would be If I started at 390, how many degrees would I need to move around to get back to where it's at?
360.
360. So can I take 390 plus 360 and get then, what's that going to be? 750?
Let's go like negative.
Okay. Okay. So what if I wanted to do this? What if I started right there and I wanted to go that direction?
You go negative.
Okay. So then I would take 30. Now I'm moving in that direction, so it's now negative 360. So negative 330 would be the same angle. Could I go
I got so many A's.
and say negative 330 minus another 360?
Yes.
You get negative 690? That makes sense?
Yes.
Okay. How many different coterminal angles are going to be coterminal with 30 degrees?
Infinite.
An infinite, okay? And here's the problem. If I give you a test question, give you a web assigned homework question or whatever, there's an infinite number of responses that would be accurate, right? Okay, so what they try to do is they try to minimize the grading process for that. So they'll say, give me the first positive angle that is coterminal with 30. So it'd be 390, right? And they say, give me the first negative one, and that would be negative 330. And those are the two that you would take. Does that make sense? So just be careful, you pay attention to that wording. They might say, give me two coterminal angles that are between maybe 700 and 900, or 700 and 1,000. Does that make sense? So you just got to keep adding or subtracting until you get in that range that they define. Okay. Now, they also like to do this. If there's an infinite number of them, there should be a tool that allows us to create that infinite number of them. And here's what we do. We say alpha, which is our coterminal angle right now, is equal to 30 plus, what was I adding to all of these?
360.
360. But now I was adding 360 one time, but then I added it 2 times, or 3 times, or 4 times, or 5 times. So that thing right there is changing. So I'm going to do what? Make it a variable. Okay. You see n from time to time. I'm going to use k. You see k quite a bit as well. Now here's the idea. Okay. That's just giving me 360 times k, and I'm not telling you what k is. So right now, if I don't tell you what k is, the assumption k is any real number, right? And here's one of the things that we talked about. We have to have an understanding of our number, or our sets of numbers. K could be 1/2 right there. Well, was 30 plus 180 a coterminal angle?
No.
No. Okay. 30 plus 180 is going to be 210, which is in the third quadrant. That's not the same thing. So k cannot be a fraction. Does that make sense? K cannot be a decimal. K has to be either a 0, because that would give me 30, right? K has to be 1 or 2 or 3 or 4. What kind of numbers are those? Okay, whole numbers. I like that. I like that answer. Okay. But I also subtracted, didn't I? So how can I, with that equation, how can I subtract? How can I make that minus 360? K would have to be what? -1, right? If I want to subtract 720, K would have to be -2, right? So now I want K to be 0, 1, 2, 3, 4, or their opposites. What numbers are those? Integers. Okay. So what I have to do is I have to write here that K is an element of our integers. Okay. And then that equation generates for us all of our coterminal angles. Now let's just be thoughtful of this. If that's the integer, the equation for when theta is 30, what happens if theta is 40? What do I change here?
30 to 40.
I just changed that to 40, right?
Yeah.
So isn't this an equation? If alpha is my coterminal angle, isn't this an equation that will generate my coterminal angles regardless of what theta is? Does that make sense?
Alpha looks like a fish.
Alpha looks like a fish. Okay, if I go to this next one, it says find angles that are coterminal with theta being pi over 3. Okay, so theta is pi over 3, which would actually be right there. And we'll talk about that later. But yesterday we did we changed pi over 3 to 60 degrees, or we changed 60 degrees to pi over 3. So that's, I know that's 60 degrees in the first quadrant, right? Does that make sense? If I want to get to a coterminal angle there, what do I need to add to it? If I want to get this ray to rotate and get back to itself, okay, so I'm going to add 360 again, right? But think about this. If I was in distances, and I told you to add 10 miles and 15 kilometers, can you do that? You get 25? Am I allowed to do that? Why am I not allowed to do that? Different units. Okay, so I have to transfer one of them, right? So here, because our answer, they want it in radians. So instead of adding 360, what is the radian equivalent of 360?
2 pi.
2 pi. Okay, so a coterminal angle here would be pi over 3 plus 2 pi. Now, and then if you struggle with fractions, you are going to get so much better at them in this class because they pretty much show up in every problem. So 2 pi is not conducive to adding to pi over 3, right? But if I write it this way,
I'm not good at fractions.
is that still 2 pi?
Yeah.
Okay, so 7 pi over 3 would be one of my coterminal angles, right? Could I take pi over 3 minus 2 pi? And give me negative 5 pi over 3? That makes sense? What would be it'd be alpha, it'd be pi over 3 plus blank, which would be 2 pi k. If k is an integer, does that make sense to our infinite number of answers for this particular problem? And now, if we're interested in, there's not a lot of textbooks that will write these things that I've got written in red here. But if I want a formula for all my coterminal angles in radians, it would be whatever theta is plus 2 pi k, where k is an integer. There's going to be, guys, there's going to be in this class, if you know anything about it, you guys worked with lightweight, you said lambda, you knew lambda was for wave functions. How'd you know that?
Science class.
Okay, so science class, you guys have worked with sine waves, okay? Whether they're light, whether they're sound. Now sound is more of a compression thing, but we can, with an oscillograph or something like that, we can change it into
Barometer?
an up and down wavy curve. Electromagnetic waves travel that way. So when I talk about Bluetooth, I'm talking about Wi-Fi, I'm talking about radio waves, I'm talking about the waves that are used to make your water molecules and your food vibrate inside a microwave. They all travel in this up and down periodic motion, which is repetitive, okay? So a lot of things that we do in this class are going to be repetitive, meaning that there's going to be an infinite number of answers within those repetitions. Does that make sense? So going around this circle over and over and over again, I will repetitively get back to a pi over 3 location. So we have a way of writing infinite answers. And there's going to be a lot of instances in this class that we write infinite answers. We'll write some definite, finite amount of answers, but then at the same time then we'll write then, okay, well this is now an equation for the infinite set of answers. Okay? That's all I've got for you today. Yes?
First time we've ever done that. You said the microwave is what to microwave?
So a microwave generates electromagnetic waves. So just like wave, like you ever walk into a room and you know the TV's on,
Yeah.
but there's no, like it's not playing or anything, but you can feel that.
Yeah.
You're feeling electromagnetic waves bouncing off your body, hitting your ears, that kind of stuff. Okay. So there's a device. I forget what it's called. I'll look it up. But there's a device in your microwave that generates this. Okay, and it agitates the water molecules that are inside your food real fast. And if it agitates them real fast, those water molecules create friction.
So you're saying.
So that friction creates a byproduct of friction. Heat. So then that heat then radiates from the inside out. That's why you can bake a baked potato like 3 minutes in the microwave, but it takes an hour in your oven.
So you're saying if the flash held a frozen hot rock in this can, it shook it really fast.
Hey, what are we hanging out?
So you take a cold bottle of water and you start shaking. Like it gets warmer. And now whether it's able for you to tell that it's warmer, but it gets warmer.
What?
That's what I'm saying. So you're still gonna multiply. So So you get 2 radians. You're still gonna multiply it by
One tough guy hit me.
that, okay? But now it's gonna be, so you're gonna take 360 degrees
What?
and divide it by pi, so there's no cancellation there. And it turns out that it's gonna give you a nasty decimal. Or you can probably write it as 360 over pi.
Oh my god. This goes to I'll get a
So, what was the degree scale?
Lucas keeps touching me.
7 pi over 6 and it's in. So, like that.
Yeah.
So then I'm still gonna multiply, so I have pi over 180. Those are gonna cancel. So now I have 7 pi squared over 6 times 180.
I don't know why.
And they do that on purpose for that reason, to make sure that we're seeing that. Good question. Well, I'll talk about those tomorrow.
Hey,
Everybody.
Andrew said hi.
Who?
Andrew.
Andrew who?
Star.
I don't know him.
He said he